Alrighty, let's get started with this. So in this video, what I'd like to do is introduce the perturbation method for solving some of our systems. What is this method? This is kind of a continuation of what we did earlier in the semester with things like Taylor series, power series expansions and stuff. It's meant to take a differential equation, which is modeling a system we're trying to model some system so we can predict what will happen in the future, whatever. And maybe this particular system is modeled by a nonlinear differential equation. Nonlinear equations are very, very difficult to solve. A lot of them are unsolvable. Most of them, even if you can sort of solve them, a lot of times what we do are kind of approximation numerical methods because it's just too difficult. We don't have any general way of solving nonlinear equations. Each one is its own entity, and you have to use specific techniques for each one individually. So these are very difficult. They give us problems as physicists. So if we could find some method that makes it a little easier, even if it might be a little tedious or a little pain in the butt, it's doable. And while you won't necessarily be able to write out the nice, perfect, functional form of the solution, you will at least get an approximation to the solution that is as accurate as you need it to be for whatever your purposes are. Do you need to be 20 decimal places accurate, or do you only need to be 5 decimal places accurate? You could have as much accuracy as you want. You just have to include more and more terms, as you'll see, or do more and more work. But each piece of that work is way easier than the original problem you were trying to solve. So the first thing we should do is, what is the difference between a linear and a nonlinear equation? So a linear equation is something, we have some, second derivative of psi with respect to x squared plus some coefficient times psi is equal to 0. This is linear. Linear. Very nice. Very easy. We know how to solve this. You bring the alpha psi term to the other side. So it would say the second derivative of some function gives us the function back with a negative. We know those are sines and cosines. We can solve this very easily. However, a nonlinear equation would be something like second derivative of psi with respect to x squared times psi plus alpha times psi. And maybe there's a square root of psi minus 1 is equal to sine of psi. Nonlinear. Very difficult to solve, if even possible. Why is it nonlinear? Because in the linear case, psi, the thing you're trying to solve for, comes in linearly to the first power. No functions of psi. It's just psi by itself. In nonlinear cases, the function you're solving for, the psi, it comes quadratically maybe. Like this first term, you've got psi times the second derivative of psi. That's like a psi squared type of thing. Same thing here. You've got powers of psi. Psi times square root of psi. That's like a psi to the 3/2 power. Here, sine of psi, that's the function, a function of psi, not just psi itself. So that's a nonlinear differential equation. And it turns out, unfortunately, that in the real world, most systems we're going to care about are nonlinear. At least the ones that we want to try to write research papers for and all of that and do experiments on, because the linear stuff, the easy stuff, people have done before. So what is perturbation method going to be all about? It's going to be something like this. Let's say you have a system, maybe we're doing electricity and magnetism, and we have a system like a conductor, a conducting shell, spherical shell, And we want to know what is the electric field, or what's the potential maybe inside this shell somewhere, maybe right here. And we know that the spherical shell maybe has a charge density sigma on it. Well, we could solve this. We could use Gauss's law, we could solve the Laplacian, whatever method we want to solve this stuff. We know how to solve it, that's fine. But what if instead we had a more interesting, more complicated problem, which was we have a spherical shell, but there's a little bump in the shell here. A little piece of the shell was taken out or something. And now we want to do the exact same problem. What's V, what's the potential, or what's the electric field, or whatever, inside of this thing, where, again, this shell has some charge density sigma on it, the outside. Well, now all of a sudden, we don't necessarily know how to solve that problem. We don't have the nice spherical symmetry that'll allow us to use Gauss's law very nicely. So this is much more difficult. However, if you think about it, notice that little bump, that little notch that was taken out of the sphere is pretty small relative to the system as a whole, right? For the most part, it's a sphere, but there's just a little piece of the sphere missing. So the theory that goes with perturbation goes like this. We know how to solve the easy problem, this guy over here. The problem we want, the hard one, is almost the same as that. And the issue, the problem piece, the thing that makes this difficult, that little thing there, is relatively small. So while, yes, it will affect the answer, no doubt about that, we're not going to get the exact same solution for both of these problems. However, the effect will be pretty small. And so we could say that the answer to the hard guy is going to be the answer to the easy one plus or minus some little difference. And it's up to us to try to figure out what is that little difference going to be. And so we solve an easy problem, and then we modify that solution by a little bit based on the hard problem. Okay. Let's actually do a real example so that we can see this in action. Now, I'm not going to do it with a differential equation here because I don't want to get messy with trying to solve differential equations and stuff. I'm going to do a nice basic algebraic problem because we're all comfortable with algebra. So let's take this example. Let's say we have the problem x squared plus epsilon x minus 1 is equal to 0. All right, so this is a quadratic equation, and I'm about to use some terms very, very loosely, so don't be confused by this, but it's just so that I can make a one-to-one comparison with what we're actually doing with differential stuff. So I'm going to say this is the nonlinear guy. Okay, obviously it's nonlinear, there's an x squared there, but let's just say this is the nonlinear guy. And I happen to know a different equation that's very, very, very similar that I can solve very easily. Let's pretend this black one I can't solve. I don't know how to solve it, but I do know how to solve this guy over here. X squared minus 1 is equal to 0. This guy I'll call the linear guy. He's definitely not linear. Again, I'm just using these terms very loosely to get used to it. It's not linear because there's still an x squared. It's quadratic for sure. But for the purposes of what we're talking about, I'm going to pretend like the right side guy, the gray equation, is the linear one, which I know how to solve. In fact, I'll do it right now. X squared is equal to 1, which says x is equal to plus or minus 1. Done. Finished. Easy. Now, our equation, the one we actually want, the black one over here, notice it's very similar to the one I know how to do. However, the nonlinearity is this term right here. That piece is messing me up because I can't anymore just bring the 1 over and take the square root. I have to do something more complicated. and I really don't know how to do it, let's say. But if this epsilon is tiny, very, very small, then what I can say is that my nonlinear equation is almost identical to my linear equation, but there's this small little correction, this small little nonlinearity piece that's going to affect my answer. But since it's a small piece relative to the system as a whole, I know the answer to this black one is going to be the answer to the gray one plus or minus some little bit. And then it'll be my job to figure out what that little bit is. Okay? That's what perturbation is going to be, and we're about to see how to do it. Now, before I do that, just so that we'll have something to compare the answer to later, I actually do know how to solve this black equation. We all do. We're just going to use a quadratic formula here. So let's just go ahead and do that. Quadratic formula says x is going to be equal to minus b, which is minus epsilon, plus or minus the square root of b squared minus 4ac all over 2a. Okay. And now I'm going to get just a little fancy because it's going to help when I make my comparison later. I'm going to rewrite it a little bit. This is minus epsilon over 2 plus or minus the square root of, in fact, I'll do the square root like this, epsilon squared plus 4 over this 2 outside of the square root. If I now bring it into the square root, will become a 4. Right? If I take the square root of the 4 on the bottom there, it just becomes the 2 on the bottom. And the reason I did that is because what I want to do is write this as the square root of epsilon squared over 4 plus 1. Okay? Now, why did I want to do that? Because if we look at this, remember, epsilon is a very small number. This is basically 1 plus a very small number to the 1/2 power. Right? Square root of 1 plus epsilon squared over 4 is 1 plus something very small to the 1/2 power. And we saw earlier in the semester the power series representation of 1 plus some small number to the 1/2 power is equal to 1 plus the thing over 2. And then some other terms of order, let's say x squared and so on. 1 plus x over 2, I think it was minus x squared over 8 or something like that, whatever. But more and more terms. Remember, this is an infinite series, but I'm only keeping some of the terms just because I don't want this to look nasty with a bunch of terms all over the place. All right, so with that power series of that square root, I could write this now as minus epsilon over 2 plus or minus 1 plus the x, remember, was epsilon squared over 4. So this is epsilon squared over 8 plus other stuff of order x squared. Epsilon squared, which is epsilon to the 4th power stuff. Okay. So, what is this? This is plus or minus 1 minus epsilon over 2 plus or minus epsilon cubed over 8. 16, I think. No, I'm sorry. What am I doing? Epsilon cubed. Epsilon squared over 8. And ... Other stuff. Okay? So that's the actual answer. And in fact, the actual full solution will be if I add up all infinite number of terms here. But again, I'm going to assume I don't have to be that accurate. I'm only going to keep a certain number of terms in my solution. And so this will be sufficient for now. So This was not perturbation method. This was just solving a quadratic equation, and then I use a power series representation on the square root part. Now what we're going to do is solve this using the perturbation method, and we're going to see, do we match? Do we get the same answer? Also notice that what we thought was true is indeed true. Over here, the linear, quote unquote, linear equation, the easy one, said the answer is plus or minus 1. Our nonlinear one, the claim was the answer should be the same as the linear one, but with a little bit of a correction to it. And what did we get? We got plus or minus 1, right here, minus some epsilon, where epsilon is small, plus epsilon squared, where that's even smaller, and so forth. So indeed, we did get what we thought would be true. The major part of our answer is the plus or minus 1, the linear part. And then we had the correction terms added to it. Okay, so back to the original question. X squared plus epsilon x minus 1 is equal to 0. All right, how do we use perturbation method? First step is assume that our answer, the thing we're trying to solve for, this x, can be written as a power series in epsilon. So we'll say x can be written like some x naught plus epsilon times x1 plus epsilon squared times x2 and so on. Okay, an infinite number of them, each one with a higher order of epsilon. Once I make that assumption, then all I have to do is stick this into x in our equation. Okay, well, if I stick that into my x, what do I have? I've got x squared, so x is x naught plus epsilon x1 plus epsilon squared x2, dot, dot, dot. That thing squared. Then I've got a plus epsilon times x, but again, x is x naught plus epsilon x1 plus epsilon squared x2 minus 1 is equal to 0. So all I did here was I took my equation, I stuck in this power series representation into the equation, and that's what I get. All right, well, before I continue, let's notice this first term here. What I'm going to be doing is I'm going to try to collect terms together that have like number of epsilon. That is to say, all the terms with no epsilons, I'll collect into one little group. All the terms with epsilon to the first power will be another little group, and epsilon squared will be another one, and so forth. That's what I want to do. To do it, I first need to mess with this guy. This guy is kind of messy. We have this infinite sum multiplied by itself. So I'm going to get a twice infinite number of terms from this. So let's go ahead and write out the first few. Again, I'm not going to be keeping anything of order epsilon cubed or above. It's epsilon squared or below is all I really care about. However, if I wanted to be more accurate, then I'd have to keep more terms. But I'm making the executive decision. I'm only going to care about terms of epsilon squared or below. Okay. So let's look at this. I'll write it out explicitly, but as you get more comfortable with this, you could just do it in your head and see the terms. But we have x naught plus epsilon x1 plus epsilon squared x2 dot, 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 times itself, x naught plus epsilon x1 plus epsilon squared x2 dot, dot, dot. I want to multiply those two things together. What do I get? All right, well, I get x naught times x naught. That's x naught squared. And then I get x naught times epsilon x1. So that's epsilon times x naught x1. And then I get x naught times epsilon squared x2. So that's an epsilon squared x naught x2. And then if I hit the x naught on the next term over there, that would be an epsilon cubed guy. But I don't need epsilon cubed stuff. I want to get rid of that. So I'll just ignore it for now and just put a dot 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 later. So I've now done x naught on all the stuff on the right I need. Now I move to epsilon x1 times all the stuff. So epsilon x1 times x naught gives me an epsilon x1 x naught. Then epsilon x1 times epsilon x1 gives me an epsilon squared x1 squared. Then epsilon x1 times epsilon squared x2, that's an epsilon cubed guy. I ignore him. So anything more to the right is going to give me bigger and bigger powers of epsilon. I'm just going to ignore it for now. Then I move to the next one. Epsilon squared x2 times x naught gives me an epsilon squared x2 x naught. And then if I hit him on any of the next terms, again, I get higher orders of epsilon. I don't care. So plus order epsilon cubed. Okay. Again, it's actually an infinite number of terms, but I'm only going to look at the first two orders of epsilon. All right, so all of that stuff is just that first blue parentheses squared. So let's rewrite it. X naught squared, okay, that's the only term with no epsilons. The next one, epsilon, well so that's done. Epsilon x naught x1, epsilon x naught x1, so I get 2 epsilon x naught x1. All right, what about epsilon squareds? Well, I've got an epsilon squared x naught x2, epsilon squared x naught x2, and an epsilon squared x1 squared. Okay, so epsilon squared x1 squared plus twice epsilon squared x naught x2. And then order epsilon cubed. So there's my first parentheses squared. Then the next parentheses, epsilon x naught plus x1 epsilon plus epsilon squared x2 minus 1 equals 0. Okay. So let's collect. Like I said, I want to collect terms. I want to group them together by their powers of epsilon. So first, I need all the terms that have no epsilons on them at all. Well, that's here. There's no epsilon. And the minus 1 has no epsilon. So those are the only two terms, x naught squared minus 1, that don't have an epsilon. Next, I want all the terms that just have a single power of epsilon. All right, well, let's see. There's a single power of epsilon there. Then I'm going to have the epsilon x naught from this guy. So there's going to be him. And then that's it. Those are the only terms that only have one power of epsilon. So it's x naught plus 2 x naught x1. All right, now I want all the things with epsilon squared on it. So what do we have? We've got epsilon squared here, and an epsilon times this gives me an epsilon squared. All right, so what do we have? x1 squared plus 2 x naught x2 plus x1. That should be all the epsilon squares. And then, of course, we've got things of order epsilon cubed, all equal to 0. All right, so now what do we have? We've got a bunch of terms added together equal to 0. However, some of these terms are multiplied by different values or different powers of epsilon. So think about what that means. How can this be 0 no matter what epsilon we choose, right? No matter, we're going to try to find these x's. So let's say we start epsilon, let's let epsilon be 1. Then I could go through and solve this equation, figure out what x naught, x1, x2, all these things should be such that when epsilon's 1, it's all these things added together give me 0. But then if I change epsilon from 1 to 0.1, those same values of x naught, x1, x2 will not hold anymore to make this equal to 0. So by changing my epsilon, I'm going to affect when it's equal to 0 and when it's not. I don't want that. I want this to always be 0. Well, the only way that can always be 0 is if each one of these terms, these groups, is 0 by themselves, regardless of what epsilon is. So, that is to say, this group here, added together, that should be 0. This group should be 0. This group should be 0, and so forth. And if that's true, then I'm going to have 0 plus epsilon times 0 plus epsilon squared times 0, and so on. So it doesn't matter what epsilon I choose. I'm just adding a bunch of zeros. That's exactly what I want. So let's go ahead and do that. How do we force that? Each group must be 0. So first thing, I'm going to have to rewrite this, so please excuse me from going back and forth a little bit. We've got x naught squared minus 1, then plus we have an epsilon times, what was this? X naught plus 2 x naught x1. Then we have epsilon squared times x1 squared plus x1 plus 2x naught x2, I believe, right? Yep. And then plus things of order epsilon cubed, and so on, equal to 0. So let's do this term by term, group by group. This group should be 0. So x naught squared minus 1 should be equal to 0. This tells me x naught should be plus or minus 1. I've now figured out what x naught is. Okay, fine. Now let's move on to the next group. This group should be 0. What does this say? X naught plus 2x naught x1 is equal to 0. Well, notice I've got x naught on every term. I'd like to cancel them, but the only way I'm allowed to cancel them is if x naught is not 0, because I can't divide by 0. But I know x naught is not 0, it's plus or minus 1 from my last term. So I'm allowed to divide them out. I divide these out and I get 1 plus 2x1 is equal to 0. So that tells me x1 is equal to minus 1/2. Notice the 1 here is not plus or minus 1's 1. It's x naught divided by x naught is equal to 1, no matter which one I chose. All right, so now I have x naught. Now I have x1. Let's look at the next one. What do we get over here? This must be equal to 0. So I get an x1 squared plus an x1 plus twice x naught x2 is equal to 0. But I know what x1 is. x1 is minus 1/2. So I get minus 1/2 squared is 1/4 minus 1/2 plus 2 x naught is plus or minus 1 times x2 is equal to 0. And I can solve this for x2. So 1/4 minus 1/2, that's minus 1/4, plus or minus 2x2 is equal to 0, right? 2 times plus or minus 1 is plus or minus 2. Bring the 1/4 over. I get plus or minus 2x2 is equal to 1/4. So x2 is equal to plus or minus 1/8. And then, of course, if we were trying to be more and more accurate, I'd now do the epsilon cubed group and then the epsilon to the 4th group and get all these x's. Once I have all these x's, remember the whole point was we said our answer x is x naught plus epsilon x1 plus epsilon squared x2 dot dot dot. So let's put this in. What do we have? X naught is plus or minus 1. Epsilon x1 is minus, so minus epsilon over 2. And then we've got plus epsilon squared x2, and epsilon x2 is plus or minus 8, so this is actually plus or minus epsilon squared over 8, and then dot dot dot. That's our answer. Now let's make sure this is correct. Let's go back. Remember, we actually got the full answer before. And what was the full answer? Full answer was plus or minus 1. So let's see, does that match? Plus or minus 1, yeah. Next piece, minus epsilon over 2. Okay, go back. Minus epsilon over 2, good. Plus or minus epsilon squared over 8. Plus or minus epsilon squared over 8. Indeed, we get exactly the same solution. And in fact, if we kept more and more orders of epsilon, we'd get more and more terms that are alike. And we get closer and closer to the true, pure solution. Although I'm not writing a functional form of the solution, I'm writing a Taylor series or a Maclaurin series or a power series. But numerically, if you gave me these values, I would be giving you the actual solution to your problem, at least to within whatever accuracy you need for your situation. This is what perturbation method is all about. You take a problem that you don't know how to do, one of these nonlinear type equations like this, or like this, and you say, well, that piece that's nonlinear, the piece that makes this difficult, if it happens that that piece is pretty small, so it doesn't affect your system too much, it's not of the same level as the system as a whole, then we could use perturbation. And we say, all right, because of that piece being pretty small, I know the actual answer is going to be pretty much like the linear guide, the easy one. This gray one on the right. That one I know how to solve. Linear problems I could solve all the time. So I find his solution, and there it is. Then I say, okay, my nonlinear problem, that nonlinearity piece is tiny, and because of that, I can assume that I could write my actual answer, x, in the form of a power series in epsilon. So this piece here, x is x naught plus epsilon x1 plus epsilon squared x2 and so forth infinitely. And then the higher and higher powers of epsilon we get, the smaller and smaller those terms are being, those correction terms. So they're going to add very little to the actual answer eventually. And so once I've made this assumption, I then stick that version of x, this power series, into my equation. And then I collect terms. I collect all the terms with no epsilon. I collect all the terms of epsilon to the first power, to the second power, to the third power, and so forth, grouping them together. I keep as many powers of epsilon as I think is necessary to get the accuracy I want. And then you have this long equation with groups of terms. And we use the fact that in order for that long equation with groups of terms to be equal to 0 always, each group must be equal to 0. So we solve each little group by itself. And what's nice is this is an iterative process. Those of you that do computer science, you know iteration all the time. And by iteration, what I mean is I could not solve over here. I didn't know how to figure out what x1 is originally. But because I found out what x0 is, right here, then I was able to get x1 on the next group. And now that I know x1 and x0, I'm able to get x2 on the next one. And then x3 would come on the next group, and x4 on the next group, and so on. You're iterating this process. You find one value, that value leads you to the next value, and then those two lead you to the next one, and so forth. You then collect all these x naughts, x1s, x2s multiplied by the powers of epsilon as you made the assumption originally. And that'll be your numerical solution. That'll be your approximated solution. And then how do you know how many terms you should keep? Well, number one, you need to have in mind what accuracy you want. Do you want to be 99% accuracy? You want to be 99.99% accuracy? Whatever. Have that in mind. And then you check. You say, okay, let's look at just the first term, the plus or minus 1. Now, if I add on the next term, the epsilon times x1, how much different is my answer? If I want, 10%, 90% accuracy, is my new answer more than 10% different than my original? If it is, you better keep it. Then you go on to the next term, the epsilon squared term. If I add that in, does that change my solution by more than 10%? If it does, you better keep it. If it doesn't, then you don't need it. Because adding it in does not get you a better accuracy than the accuracy you were trying to have anyway. It will affect it. You're getting closer to the right answer. But when let's say you're weighing an elephant, does it matter if the elephant weighs, 3,000 pounds or 3,000.000004 pounds? No, you don't care about that last little bit. It is more accurate. It's actually more realistic. But in terms of whatever it is you're doing, you're thinking about, an elevator system. You don't need to worry about the 25th decimal place accuracy anymore. And that's what we're doing here. We keep as many terms as we need, and we keep keeping them until keeping the next one does not change our answer in the accuracy percentage we're actually worried about. You keep all those terms and you say this is approximately the answer, and that's the answer you use for whatever system you're working with. Okay? So that's the perturbation method. Very, very powerful, very important, especially as you go to graduate school, because when you get to graduate school, you're not working with baby equations anymore. You're going to be dealing with nonlinear stuff, especially if you do research, you write a thesis or a dissertation. Likely your research is on some nonlinear problem because they haven't been done yet. And one of the methods you may go to use to solve that problem will be perturbation. I did. I wrote 3 publications on my research for dissertation, and one of them specifically used perturbation as a method to try to get a solution. So it's a real world thing. We use it all the time. I wanted to do this algebraic version to avoid the mathematical complexity of differential equations, but the same premise holds. It doesn't matter that it's algebra instead of differential equations. The method is still the method. All right, so hope this was helpful. I will see you next time.